today our task is to create a neural network from scratch. Now, what does from scratch mean? It means we are not going to use any building libraries like TensorFlow or PyTorch. We are just going to use NumPy and pure maths. So, machine learning, as someone who knows about machine learning, knows how much maths you have to use if you are not using a library, right? So I will not go in that much detail about maths, but I will give you an overview how does the maths looks like and how we implement it in the code. Okay, so what is this? This is a database. This is a very standard database when we are using for a tutorial or application for our beginner projects. So this is a image recognition classification, right? So it is a multi-classification model data. It has 10 classes which has a number from 0 till 9, right? It is of 784 pixels. It have, for example, this 6 image has a 784 pixels. So one image is 28 by 28 image, right? Now how does a single data look like? As I said, it is a 28 by 28 image. This is a 3, as you can see. So we have to tell the computer that this is a 3. Now our pixels are represented in the number between 0 to 255. So it is a white to black scale. Okay, so 0 is fully black and 255 is fully white, and between them there are shades of grays, right? Now what is our training data set? It is a bunch of images. Tens of thousands of, actually we are 20,000. This is an example. We are using like 40, somewhere around 40,000 image, right? Now uh, okay, so what does our training data look like? Okay, so it is in our data set. It is not like perfect images, okay, because the computer doesn't understand images. We have to convert them into a vectors or numbers. Vectors is something, array. Vectors is nothing but an array or list, as you whatever you want to say. So this whole x1 thing is one array, vector, list, whatever you want to call it. So what is this? So this whole x1 thing is one array, vector, list, whatever you want to call it. So it represents a full image, right? How does it represent? In this format, 284 pixels, right? So it has 284 like numbers in one array. So it represents, so for example, if it is here the pixel, this represents zeros because it is fully black. So this whole 28 plus 28 plus 28, this row would be black. Now here it is shade of a gray, so it will convert it into a number and assign it to the assign it to specific color and put it into an array. So that's what image converting into vectors look like. Okay, we will see in the our program, our code, how does it look like. Okay, so this x1, x2 and x2 till m is our number of images. I will call it m, and okay, so keep it in mind. Okay, so right, so we have m images and all of them are x1, x2, x3, all of them are of 784 like numbers length. Okay, so our image, this matrix becomes m cross n because m is from this numbers column, rows, and into columns which are 784 columns. But for our convenience and for the model's convenience, we want it in a transpose way. Transpose is nothing but, if you know matrix, you know what is transpose. It is nothing but column to row and row to column. If we make the column into a row and the column into a row, okay, row into a column. So this will convert into this. So of straight line, now a column will represent an image and the row will represent the number of elements, right? So our image becomes n cross n. Okay, now let's get into the neural network. So our neural networks architecture is very simple, because if we create a larger neural network, it will be very complex. So this will convert into this. So of straight line, now a column will represent an image and the row will represent the number of elements, right? So our image becomes n cross n. Okay, it is for our convenience and also for the model's convenience. The data doesn't change at all. Okay, now number of columns equal number of images in the training data equals to n. Now let's get into the neural network. So our neural networks architecture is very simple, because if we create a larger neural network, it will be very complex. So the back propagation would be very complex. So we'll see about back propagation. So it will be very like the code will be lengthy, the calculations would be lengthy, and all of that, right? So for like education purpose, we will only use this. you can create your own. If you understand the maths in this video, you can create your own. Okay, so what is our architecture? First layer, zeroth, not first but zeroth layer, it is our input layer. If you know neural network, you know that there are three types of layers in neural network. First is hidden input layer, second is hidden layer, and third is output layer. Okay, so input layer is nothing but the inputs. Okay, so for example, here we are inputting, if we are inputting one image, we are inputting 784 like pixels numbers. Okay, so we have 784 like numbers of inputs. Okay, so the nodes, a zeroth number have 784 neurons. What is neurons? Neurons or node, whatever you want to call it. A neuron is nothing but a simple model. Okay, if you represent a neuron, you will write a like sigmoid function or a classification function or a softmax function. Okay, linear regression or any other logistic regression. So that one model is one neural network, neuron. Okay, and by combining multiple neurons, we create one layer in one neural network, and we combine those multiple layers and we make a neural network, right? So that is what neural network is in a nutshell, right? So the first layer is nothing but an input, second layer is a hidden layer, third not second, the first layer is hidden layer, second layer is hidden layer, and third layer is output layer. Okay, so for minimal approach, we will keep both of them of 10 neurons. Okay, so one layer of first layer will contain 10 neurons, second layer will contain 10 neurons. Okay, so what does that mean? Here we are using dense model, right? Dense means every single parameters or output will go to every other neurons, right? And every other models, and it will throw out a number, and that number will also go to every other neuron in the next layer, right? So that is what dense model looks like. Okay, now the zeroth layer has 784 because 784 numbers. Second, the first layer has 10 neurons, second layer also has 10 neurons, and third layer has only one neuron, which is the output. It will give one output, so we have one neuron. Okay, now let's jump into our forward propagation. What is forward propagation? Forward propagation is simply what you code in PyTorch, right? You code the first layer, second layer, third layer, right? That is what forward propagation is. Okay, there is nothing more to it, but we have to write the equations because we are not using PyTorch or TensorFlow for this, so we have to write the equations. So the equations are really simple. The main equation is the z's equation, right? I will call this z is nothing but what we call parameter, which is made of other parameters, which is w and b, which used to adjust our like result, so it gives us a result, right? Okay, so the first, so a0 is equal to x. A0 is, a will represent the model's activation function, so it is a activation function is nothing but type of model we are using at that neural that layer. Okay, in the neural network at a particular layer. So first is the zeroth index, the zeroth layer, which is just an input layer, so we will just assign it to x, which is a 784 into 1. Okay, so we are inserting one image at a time, so 784 into 1, right? Now the first layer, we start from z, right? So z1 is equal to w1 into a0. So here what zw takes as an input is the input from previous layer. Okay, every z at every layer will take input from its previous element, and that layer will go give it the output to the next layer, and so on and so forth. Okay, now so this z is taking this a0th layer, so we have represented it here. So this input will taken here. So we will assign it. W is nothing but weight, and B is bias. If you know machine learning, you know both of this. These are the base, like the core of a model. Without this, the model is nothing, right? So W and B. So W and B decides how much that particular pixel or a feature is doing something to the answer, right? How much it is affecting that answer. That is why we have W and B's. Okay. So W for particular pixel is different. Okay, so we have 784 like pixels, right? For every single pixel, the w will be different. Okay, so here 10 into 784 is because we have 784 pixels, so for every pixel we have a particular w, but 10 represent the number of neurons. For example, neuron 1 has 1 into 784, neuron 2 have 1 into 784, so if we combine all of them, we get a 10 into 784 w is nothing but weight. We will get an like array or a vector, right? A0 is nothing but this, we already discussed it, and B is same for every single pixels or features, right? But it is different for every neurons, so it is like 10 into 1. Okay, so 10 neurons or 10 biases. Now the first activation function, first layer, we are using the ReLU layer, ReLU model. Okay, ReLU is a very important model in machine learning or neural network for say. It is basically used always in the hidden layers. If you see any like neural network architecture, you will see that almost all the hidden layers are ReLUs. ReLU is nothing but a linear regression, but with some efficiency. It is efficient and effective, right? So what is ReLU? I have it here. ReLU is nothing but this graph, and it is similar to linear. Okay, so it is like this and going this, because when the number is 0, right, less than 0, it stays 0, right? If it is less than 0, it stays 0, and when it is greater than 0, it will be that number. So the ReLU's equation is max of 0 comma x. Okay, so all the negative number it will neglect and give us 0. Okay, now we are using for the first application layer activation function, ReLU function. Okay, ReLU function is nothing but like this, max of 0 comma x. Okay, so for the input we will take z. Okay, so z it will be the input for the our first layer. Okay, so that is first layer done. Now second layer will be z2. Z2 is equal to w2 is a1. This is the input for the next layer, and plus b2 we already discussed about. Here 10 into 10 will be the dimension, because for final hidden layer we are using a softmax. What is softmax? Softmax is a multi-classification logistic model. So what is it? Like if you know about Sigmoid, it is a binary classification. Like if we have only two possibilities, like if it is a cat or dog, if it is spam or not spam, if it is a fraud or not fraud. So in that case, we use a sigmoid function. So here you can see the sigmoid function. So this is what it looks like in a graph, right? So if, for example, this is a threshold. Before this is always like in a particular area, yes area, and sorry, after 0.5 it is a positive area, after before 0.5 it is a negative area. Okay, so for sigmoid the equation is 1 by 1 plus e raised to minus x. Here x is z. Okay, so this is x, so w a plus b, that is x, so e raised to minus x. Okay, now softmax is because you are using sigmoid because you have binary classification. So for one, it will give you a possibility that this percentage I am sure that it is this thing, and this percentage I am sure it is this thing. Okay? And by that data you will decide which is the true one. Basically whichever one is the greater one will be your choice. But in softmax you will get an array which will contain how many elements, the number of like classes you have. For example, we have 10 classes here, so we will get an array of 10 elements which will contain probabilities of being that number. Okay, so we have 0 to 9, right? Perfect. So here y will give us this sum output, and this will be output from a0, right? Now a1, sorry, a1 would be this. Now if we put it into softmax, it gives us this thing. Okay, so equation is this. For example, you want to find the probability of it being a 0, so e raised to z0 upon sigma of e raised to z of I. So it will calculate 0 till I, it will calculate the possibility of them and combine it and divide it by that. So okay, sorry, the sigma would be here because it is giving us a 1 probability. So we know in statistics probability always add up to 1. Okay, for all of the possibilities it is already add up to 1. So the sum of this whole thing is 1. So it will give us 10 classes, and if you see, if my y is 7, if I am inserting a number 6 as an image, it will give me a 0.8 70% sure that it is a 6, so highest probability is 6, so our output would be, prediction would be 6. So that is softmax. Now the main thing which we need to apply, back propagation. HS is like we need the W and B, right? You know how important W and B's are, but if W and B are something random, we don't need that. Okay, we need something which works. We need to optimize that. So for that, back propagation is used. In forward propagation, we go from input and go to output, right? The equations are from input through output. Okay, but in back propagation, we go from back output to input, right? First we perform forward propagation. Now after performing forward propagation, we get the last output, right? A3's output. Now that A2 output would be used as an equation for going backward. Okay, and we will go to the final number. Okay, as I said, initially we start with a random value. The optimization is done using backward propagation, right? We need to optimize these four things: w1 b1, w2 b2. Now this is uh, and before that we need to convert the outputs or the predictions or actuals into like one hot encoding. What is one hot encoding? It is nothing but a presence or absence of that class in that image. Okay, so for example, for this example we have 10 classes. So for single prediction it will create 10 like array of size 10, and for every number it would be 0 except the present one. For example, here the 2 is present, our input is 2, right? So our actual prediction is this one. Okay, so this is present. Okay, 1 is present, so it is now converted into an like 10 array. Now let's look at this. It looks scary, but if you understand it, if you uh, like have studied derivations, you won't be that much afraid of this. Okay, so here first we start from, as I said, we start from dz. Now here we are calculating dz's. Okay, because what we need is dw's. Okay, derivation of w, right? We don't need w's, we need derivation of w to optimize w's. We will understand it afterwards, we will understand all of this. So the wz2's equation is nothing but a2 minus y. Okay, this is always a single equation for dz, which is a2 minus y. It is derived from this equation, right? So a2 minus y, if you want to understand in the like layman's language, a2 minus y gives us the difference between the actual output and the predicted output, right? So it will give us a difference, right? So if I have predicted 4 and answer is 2, the difference is of 2, right? I'm just giving an example, it doesn't work like that, but I'm giving an example. So if the prediction is 4, and the actual output, what it should have given is 4, then the difference is of 2, right? So it will have that number. So that much how wrong I am. So from this I know that, and by using that we'll calculate w, that how much do I need to adjust the w so this error would go away, right? So for that this equation is used, because we are using a softmax function, right? So dw2 is equal to 1 by m into d of z2 into a of 1 of transpose. So a1 we know already, right? Because we have calculated all of this, right? When we calculate forward propagation, we calculate this whole things, right? A0, a1, a2. So to find w2 we need a1, because we need the mistakes we did in the previous like array or model, right? So what we'll do is here is dz2 into a1 transpose minus, right? So if we simplify it, if I put the z's value, it will be 1 by m into a2 minus y into a1 transpose, right? Okay, the equation is same for b, but here two changes are there. In b2 we add a sigma in it, and we remove the a1 transpose from it. Why sigma? So as I explained before, for every neuron, for every pixel, there is a different w. So we need a specific w for all of them, right? So this is good for that. We will calculate for all the pixels and for all the neurons a particular w, but d we need only one. Okay, for whole neuron, for one neuron we only need one b. So we sum all of the dz's to make one like b, and we divide it by m, so it averages out, right? So uh, the final equation is 1 by m sigma of a2 minus y, right? Now we have calculated w2 b2, sorry, dw2 and db2, so that is good. Now the next one, dz1, right? So this is for the ReLU function, right? ReLU activation function. So dz, which is equal to w2t, which we got from here, we'll transpose it, and dz of 2, right? Dz of 2 into ReLU dash. So here the difference was, because it is the input, the output layer, we only have one, we don't have w's, but here we have w's. If we had 3 layers, here w z's equation would be similar but little different, right? So w2 transpose into dz of 2, which we have calculated here, and dot product of ReLU dash z1, right? Z1 we will calculate from this. Okay, z1, sorry, we have already calculated z1, so it will get it from here, right? So ReLU, the ReLU function is nothing but something like this. If we want to write the ReLU in program, it would be, if it is like the z is greater than 0. Okay, so if it is greater than 0, it would be 1, right? So boolean, here we get a boolean value 1 or 0, 1 or 0. So if z is greater than 0, if it is not negative, it will give us 1, or else it will give us 0. So this is basically what we write in the program, right? Now we have calculated dz1. Now we will calculate dw1. So this whole calculations are done by very long derivation equations. So all of these are chain rules we use here. So if you want to like understand it more, you can watch videos. Stanford provides really good content regarding this. Okay, and we have calculated dz1. We will calculate now dw1 and db1, right? So dw1 is similar to dw2, so 1 by m dz1 into a0 transpose, right here. So dw1 equals to 1 by m dz1 into a0 transpose, right? So if we simplify it, because it is a ReLU function, this is the equation. 1 by m, the z, if we put the z, 1 by m w2 transpose dz2 dot, this is a dot product, ReLU z1 a0 t, right? These all dashes are transposes. Okay, if we more simplify it, it will become 1 by m w2 transpose into a2 minus y, okay, dot ReLU dash, because dz2 is nothing but a2 minus z, so we will taking their value from that. So this equation we get. Now the final equation, which is the db1. So 1 by m sigma d z1 is equal to 1 by m sigma w2 transpose. So we just put the equation of this. So it will be the sigma of w2 transpose a2 minus y dot ReLU dash z1. Okay, so you can take a screenshot or whatever you want if you want to just understand and look at afterwards, right? So how would we achieve the optimization part using these values, right? So here is what we use in gradient descent. What is a gradient descent? It is a technique to like minimize the loss using W and B's and using the learning rate. What is learning rate? It is alpha, which is learning rate. It is how fast our model should run. Now you will say we'll just keep the learning rate very high and the model will learn very fast, but that's where the problem comes. If you keep it too low, the model will run for very long time, and it will work very slowly, and it will consume very much power. If it is very fast, then it will bounce around. If I want to show you how it will go, so if I want to draw a gradient descent in a 2D form, this is what it looks like. Gradient descent above, right? So the W where the minimum loss is achieved is here, whereas the x-axis is 0. So here the loss is 0, right? Y-axis, sorry, okay, y-axis is 0, right? For example, our current W is here, right? And this is very far from that, so we want to reach here. If it is very slow, it will go very really slow, baby step, very little baby steps, right? It will go very slow. But if it is very fast, it will bounce around. It will directly jump here, then it will see it is too large for the case, and it will go here. It sees it is very large again, or small again, so it will go here, here. It will bounce around. It will bounce around, and we don't really know if it will get to the optimal thing, because this thing really don't get us that far. So it is not recommended to take the learning rate to be very high. So our learning rate is between 0 to 1. So here we will take a learning rate to 0.1, right? So we will take random W1B. So how would we optimize our W1? So our W1 is random, right? So we'll take a random W1, and gradient descent will run a loop until it finds a optimal W, right? So if W1 minus alpha into dW1, which we calculated here, okay, this is a number which will decrease or increase the W1. This dW1, if we want to write a equation, it is a different equation for different models. So this is not really the dW1 equation, okay, it is, but dW is written in like very efficient way. It is actually dl upon dw, right? Oh, okay, I have written here. Okay, so what it is, what is L? L is the loss function. How much loss are we making? There is an equation for it, like mean square method we have, then other cross validation method we have. Different method for them. So for that we calculate delta L upon delta W2, right? So this calculates a number which is either plus or negative or positive. So according to that, our w1 changes for every single recursions, every single loop run. So whenever we need meet a particular, like, this is nothing but epochs, right? The equation is same for all of them. The change where it comes is dl by dw. It is different for linear regression, it is different for logistic regression, different for softmax, different from ReLU. So okay, so it is different for all of them, right? Now we have calculated all of this. Final w1 b1 w2 b2 we will get would be near to perfect weight and bias which we need to get an almost accurate answer, right? So if you want to see some calculation, I have written here because I have to derive these things. So I didn't have this equation in back of my mind, so I have just written it here. Right now, random will take random W1B. This is our workflow. Random W1B will take. Now go back to forward propagation. We will first run the forward propagation, then we do backward propagation, right? To calculate W1B, optimize it. Then forward propagation again backward propagation, and so on. This goes on for how much time we need to perfect our W1B and how much like layers we have. Okay. Now this is the explanation. So let's start with the coding. Let's start. So my data is here, training.csv. It has like 40,000 data. So let's load the important libraries, which are only NumPy, Pandas, and Matplotlib. We don't need PyTorch or TensorFlow or Jet on any of them, right? So let's import the data. Let's load the data. Now let's see what our data looks like. Okay, so these are the labels. So this is what that particular image represents. So for example, the label one, so that means this whole column represents a number 1 in that particular 28 by 28 image. So as we said in the video, in the explanation, it has 784 pixels, right? Why is this not right? So as you can see, 783. So because it is starting from 0, it is here 783, right? So that's our data. Okay, so right. Now let's see the how many data we have, right? We are shuffling because we don't need data in a particular order. For example, in some data set there would be all the ones first, all the twos second, all the threes third. So we don't need that. We just want to randomly shuffle this, right? So our model can have a raw data and it can train on that data, right? Sometimes the model can overfit if the data is in a particular order. We don't need that, right? So right, print our shape is this. So we have 72,000 sorry 42,000 data images, right? Now we have data, this is our data set. Now we need to divide them into multiple like parts. So we have testing data, training data, and testing data, right? So we are dividing into we will take 80% of the data as a training data, so 0.8% of data, that means 80%, right? So 80% of data is training data and the other half is testing like validation data, right? Now we will have to divide it into the y part and x part. What is y part and x part? X is the input and y is the output, right? So x is the whole pixels 0 to 783, and y is the output, which labels which we discussed about. So where was the label? At the first index. So we will need all of them from the training data set, and we will just need the first column, only the first column. So this slicing gives us only the first column, and we will take the first we will take all the columns, but we will only start from the first index for second column, right? So pixel 0, we will start from pixel 0, and we are transposing it. As we said in the video, we don't want this, we want this. Okay, now what we are doing here, we are normalizing the data. What is normalization? We will convert the data in 0 to 1, right? So right now our data is in between 0 to 255, but we don't need that much. So it will give us a very like vague answer. It won't give us an good answer, right? So we will normalize this by dividing the by the highest number. So we know by our like explanation the highest data is 255, so we will divide it by that. Same for validation data. We will take, if we print our parts, so the size is, if because we transposed it, this 45,990 comes afterwards, so it is the validation data. So this is how much we will be keeping aside for testing purposes. So validation data is of only one like column, so 45590 by 1, and the same for this, right? Now let's start with our main thing, model preparation. So our first function is initialization of w and b's. So we will take random values because we are for w1 how much we needed. We needed like 10 by 10 by 3 sorry 784. Why? Okay, so why we need 10 into 784? Because we saw in our short in our like explanation, 10 into 784 what is what we need for our w1, right? Because it has like 784 pixels from the input array, and for every single like thing we need that, right? So first W and B would be this, and all of the numbers would be randomly generated. So B1 would be 10 10 comma 1 because every neuron gets only one B, right? And W2 is 10 into 10 because we will get 10 inputs from the previous layer, and for every layer it is different, so 10 comma 10. And B2 is similar to above, 10 comma 1, right? So we will return this thing so we can use it in next thing. Now the second thing we need to do is define define the models which we are going to use, right? So what are the models we want to use? First is the ReLU method. Second, softmax, right? So we take x as an input, and we will see which is the maximum. So if x is minus in negative, so 0 would be greater, so it will return 0. And if the x is greater than 0, it will return that value line where we just get the positive numbers, right? And the softmax calculation, we will just get the z1 z1 not z1 z which we have calculated, and we will calculate exponential. Okay, so e raised to z1, e raised to z1. Okay, so np dot exponent of z divided by sum of np dot exponent of z. Now z here is an array probability, right? So it will calculate that and give us. So we'll get an array again, right? Now because here everyone here we will get a singular number, not an array, and that singular array would divide everyone with this number, right? Every number. So we will get a percentage of which is the answer. Now next thing is forward propagation. Simply we will write the equations which we discussed here. So z1 is equal to w1 dot of x. So dot is the function of numpy, so it will give us a dot product. So first we will create a function of forward propagation. What we will divide is w1 b1, w2 b2, and x, right? So z1 equals to w1 dot of x because z1 will take the input row input plus b1, right? Now a1 equals to ReLU of z1. We have already created the first activation function of our model is ReLU, so the z1 will go into a ReLU function which we have created here already. Now second we have to calculate the z2. Now z2 is equal to w2 dot of a1 which we have calculated here, and plus b2, okay, which we will get from here. So the first time it is randomly generated as we know, right? Now a2 equals to softmax calculator, so this is the softmax calculator, and we'll just input the z2, right? Simple as that. Now we have done that, and we'll return all of them, z1 a1 z2 a2, because this whole thing would be used in backward propagation, right? For the backward propagation, first we have to create a one hot converter, right? So we'll create a one hot converter. We'll just input the y, okay. One hot y is equal to np dot 0 y dot size comma y dot max plus 1, right? So what is this doing? So it is creating a shape of that particular array. So it is a bunch of zeros, all of them are zeros. Now one hot y of num and p dot arrange y dot size comma y equals to 1. So what does this basically do? It gives us it converts that zero, a particular number index where it should be 1, it is present. For example, the y c, so at that position the 0 would be 1, and we will just return the transpose of it because we want the transpose of it. Okay, now for backward propagation, what we need? W1 b1, w2 b2, z1 a1, z2 a2, and x and y, right? First of all we will convert the y into one hot, right? Now first of all let's just calculate the z2. What is the equation for it? we saw it here, simple as that, a2 minus y. So we'll just do a2, which is from here, which is our final output, minus 1 hot y. Okay, 1 hot. Where is this z1 a1 z2 a2 coming from? Here, right? Now we have calculated z2. Now we will calculate dw2. What is dw2 equation? 1 upon m, okay, into dz2, which we have calculated here, dot of a1, which we'll get from here, of transpose. So we'll transpose it and multiply it as we saw in the equation, right? So we have our w2. So db2, which would be equal to 1 by m into np dot sum dz2, which we saw here. These two equations we just implemented them. Now for calculating dz1, we will just write the equation, which is w2 dot z dot t, which will convert it into transpose dot because we need the dot product with dz2, which we calculated here, into the ReLU function. This is the ReLU function, which simply gives us, if it is 1, then it returns 1, and if it is 0, it will return 0. If it is negative, it will return 0, right? So this is what ReLU function does. Because why is it working? Because if it is negative, this number is negative, then the whole thing would be 0. But if it is positive, it is the x, right? So dw1 equals to 1 by m into dz1 dot x dot t, right? Because dw1, what is dw1? 1 by m into d1 dot x dot t. We already know it from here, this equation, this whole equation, right? So w2 dz2 into a0, right? So that's what we are doing. So x dot d is what a0 is, and d1 is simply just sum all the dz1s and divide by m. So we will return these things. Now we have written this. What do we do now? We just adjust this w and b's, right? So we have random w1 w2 and b1 b2, right? So we'll subtract some amount or add some amount to accurate our w1 w2 b1 b1. So update parameters. So input would be w1 b1 w2 b2 dw1 db2 db1 dw2 db2, and the learning rate, right? So w1 equals to w1 minus learning rate into dw1 db1 equals to b1 b1 minus learning rate into db1, and same for both of them, and we will return the calculated w1 and w2 b1 b2, right? Now this is for calculating how our prediction is accurate with the particular, and what is the accuracy of our prediction. We will need this for visualization purposes. So let's create our gradient descent. What is gradient descent? This is gradients, this whole thing, this is a gradient, this is a gradient, this is a gradient, and this is a gradient descent. So what it does is iterate through all of them and call forward propagation, backward propagation, forward propagation, backward propagation multiple times until we reach a particular number, right? So we'll create a function gradient descent x, y, alpha, and iteration, right? So this four we need x and y, alpha, which is learning rate, and iterations, how many times we want to run this, or epochs in machine learning terms. So w1 b1 w2 b2, which we call initialized parameters. So this function would be called, so random w1 w2 b2 would be created. Now for I range of iterations, how many iterations we have called, and z1 a1 z2 a2 will calculate from this, right? Forward propagation, we will get z1 a1 z2 a2. So we'll get these variables. Now we will use these variables in calculating w1 dw1 w2 b1 db2. So we will call backward propagation. So this function would be called, and this variable will be our answer. So we'll input our w1 b1, which we have already seen, w2 b2 z1 a1 z2 a2 x and y. Now we will update this parameter using the a1 z1 and all the parameters we have got, and the alpha rate we will input, right? Alpha rate. Now this is for like calculating how much accurate our model is. We'll see when we run, right? So, and next is we are just going to run this, right? So this is running the gradient descent, this final function which needs to accurate our model. So x train, y train, 0.1, which is our learning rate, and 1000 is our epochs. 1000 epochs we want to run, 1000 times this should run, right? We'll just run this thing and hope we don't run into any errors. So if we run, so let's finally run this. uh, so as you can see, this prints the iterations and the accuracy of both. So we are, this is the least amount of like accuracy, 0.1%. So let's wait for it to complete. Till then I will explain this whole thing. So for example, let's if you want to like if a specific number is being used, or if what is that specific number, and we want to see what output it gives us. So this will run a forward propagation and just give us an answer y index. So what would be our prediction? So our prediction would be a2l, right? Because a2l is what we will get from that number, and we will get actual label is y of y level. So we'll compare them, the predicted value and the label value, and finally uh, we will draw our image in a grayscale in graph and see if that what is that particular number, right? And this is how much accurate our model is. That this will give us how much accurate our model actually is, right? So let's see, we are on 620, so half of it is done, and we are already at 84% accuracy. So that is very good. This is the reason we take a very small, not very small but not also very large amount of learning rate. This is moving on 0.1% of like learning rate speed. If we increase it to like 0.5, this will jump around very uncontrollably, and it would be very bad. So as we can see, it is stuck at around 8.6. It will, I think it will go up to 8.7. So 87% accuracy it will go to, which is not really bad considering it is built from scratch. This means we have done all the calculation correct in the backward propagation, and we are getting a very good response. So we are around 86.8%, and our model is completely done training. And let's run this. So as you can see, our prediction is 3 and our label is 3. This is the image which we fed, and it was accurate. Let's test for some another image. Let's say 1000, which because we have 4000 images as a validation data. So as we can see, it is predicted 7 and actual label is also 7. If we put a 5 between this and run this, it is 0 and it is actually 0. Now let's see how much accurate our model is actually. So as we can see, our model is 86.9% accurate, which is really good. Right? If you want to see how much this model is accurate compared to the model you create using PyTorch or TensorFlow, you can check that also. It would be around this only. Like it can go to 90 or 7 point or 80, 88 or 89, right? Won't be far away from our model. So that's it. That is how we create a perfect model for neural network with 2 hidden layers. And if you liked my explanation, you can check out my YouTube channel, and also my Twitter and other handles, and you can repost it or re-upload it or share it or repost, upload it, whatever you want to do, you can do that. Okay, so that is it for this one. I will try to make more videos. I have some projects in my mind, and we will see if we can make it. So thanks for watching this, and hope you liked it, hope it helps. And if you really want to understand the maths, the backward propagation and all of that, I would suggest you look into maths or machine learning maths really in deep, so you can understand them. It is very crucial if you are if you want to go into like research field, or like you want to see how the internals work. You need to like know what does it actually work behind the back. Okay, so that's it for this video. See you next time.